All right, so picking up here on page 48 in the notes, we're going to now actually apply some formulas to these. Again, the derivations for these are in your textbook. It really just comes down to making triangles and looking at angles, okay? If you're very interested, you can read through section 13.5 of your textbook. In the interest of time and for what we really need out of it, I'm not going to derive them, okay? But you can see kind of the remnants of what we were talking about in the theory, right? Notice n is here for constructive interference, and n minus 1/2 is here for destructive interference. Just building triangles, using that path difference to make a triangle, where we can then talk about sine theta in terms of the wavelength and the slit separation. Okay, so this is the equation I would recommend you always use. Okay, again, really it's one equation. You just have to know when it's constructive, put in n, when it's destructive, put in n minus 1/2. Okay, this always works. This is not an approximation. This one down here is an approximation. It works pretty well when the angle is very small. However, there are times, in fact, there's even one in your textbook from your practice work for this week, where they shouldn't have used this one. The angle was not small enough to use this, and they did. So their answer is actually wrong. You'll see that in my solutions. So this one, what this one is really useful for, okay, is to find out what happens to one variable when another is manipulated. This one works really well for that. Okay, it's a little easier because X, D, N, and L are just easier to play with. However, this one also works. You just have to first figure out what changing those will do to theta. Okay, just going to define these. Okay, so again, going to emphasize that your formula sheet does not give you two formulas for constructive and destructive. It gives you the formula for constructive. You've got to know to put in that minus 1/2 for destructive. Okay, so I'm just going to draw a picture here to help us visualize what all these variables are talking about. So I'm going to draw a setup for a double slit experiment. So D is the distance between slits. So this is D, D being the distance between slits. Then if we're shining light in here, okay, we have our screen over here where our diffraction pattern is going to be produced. Then the distance from the slits to the screen, that is L. Now if we shine in some light, okay, with wavelength, whatever, okay, of course, lambda is the wavelength. But what we will see is we will get a interference pattern on the screen. So we will always see the central maximum, okay, but then we will see a first order bright spot, third order bright spot, whatever, right? Second order bright spot, first order bright spot, second order bright spot, third order bright spot. So we can kind of draw a line from the very middle to the central bright spot, the central maximum, okay? Now, if we're looking at, say, our first order bright spot, okay, then we could draw a line there as well. Notice how we kind of have a triangle going here, okay? So this angle here is the angle theta that we're talking about. The angle from the middle that you have to kind of look outwards to get to your next bright spot. So you can imagine as we go n equals 1, n equals 2, n equals 3, theta gets bigger and bigger and bigger as we have to look wider or wider or wider, right? Quick note here, because of the symmetry here, theta here will be the same as theta here. So it doesn't matter which side of the central maximum you choose to pick as your n equals 1, it's all the same. Which brings me, of course, to n. So we define the central one as n equals 0, right? There is no path length difference. It's n equals 0. The first bright spot is n equals 1, and then n equals 2. Same thing down here, n equals 1, n equals 2, n equals 3, okay? And the same goes for the dark spot. So this is the dark spot number 2. This is dark spot number 1, dark spot number 1, dark spot number 2, dark spot number 3, okay? So again, n equals 1, n equals 2. It's just that when you plug those in, you're going to have to think about subtracting 1/2, okay? The last thing I didn't talk about here, okay, is x. The x is the distance over here from your central maximum to where your bright spot or your dark spot appears, okay? So this is x, or this is x, okay? So notice here, we have a triangle then, right? What's this length here? Well, this is L. So how could we get theta if we were only given x and L? Well, tan theta, right? We want x, that's opposite, over adjacent L, okay? That will be important because, again, if you're not using the approximation, you're going to need to find theta, right? And honestly, to know if you're allowed to use the approximation, you have to find theta anyway. So in other words, theta is the inverse tan of x over L. That's going to be important. We're just looking at this triangle here, right? So this is L, This is x, the distance from the central antinode to. Okay, so now that we've defined our variables, let's just jump in. So EMR is shown on a double slit apparatus with a spacing of 3.1 times 10 to the negative 5 meters. So what is that number? Well, that's D. That's the slit spacing. Okay. The distance from the central maximum to the first antinode is 2.98 times 10 to the minus 2 meters. Let's go ahead and draw this just to get a feel for what those variables mean. So we have our slits, we have our screen. So draw the central line there. Okay, this would be where the central bright spot would be. And it's saying the distance from the central maximum to the first antinode. So our first antinode will be, let's say, there, right? Of course, there's another one on that side, but we're going to use this one. So this is n equals 1, saying that that distance there is 2.98 times 10 to the minus 2 meters. So x, right? That's x. If the screen is 1.62 meters from the diffraction grating, so the screen is 1.62 meters from the diffraction grating, so L, then what is the wavelength and type of EMR used? So we are not going to use the approximation, although honestly here we probably could and it would be okay. Again, the approximation comes from the fact that for very small angles, tan theta and sine theta are about the same. And since tan theta is x over L, then sine theta can just be replaced with x over L. That's where you get lambda equals xd over NL from. I would just say don't risk it. It's not that much more work to just use the safe one anyway. Okay, and that will always give you the right answer. So again, this would be theta, okay? And we want to know what is lambda. So first, let's find theta so we can put it in. And so tan of theta, right, because we have opposite and adjacent, equals x over L. So we get that theta is the inverse tan of 2.98 times 10 to the minus 2 meters over 1.62 meters. That gives me that theta is 1.0538 degrees. Okay, now we're ready. Now we can plug that into step 2. Lambda equals d sine theta over, okay, now are we at a bright spot or a dark spot? We're at a bright spot, right? The first antinode. So that is a constructive interference. So we're not going to use n minus 1/2. We're going to use n, okay? So then lambda equals 3.10 times d sine of the angle we just found divided by, we're at the first bright spot. So we're at n equals 1. I got that lambda equals 5.70 times 10 to the negative 7 meters. Okay, bonus question. What kind of EMR is this? Okay, whenever I see times 10 to the negative 7, I'm right away thinking probably visible. Good chance it's visible. Okay, so 5.70 times 10 to the negative 7, another way of thinking that is 570 nanometers. Okay, which sure enough is smack dab in the middle of the visible spectrum, which is 350 to 700. It's definitely visible. That would be yellow light. So yellow light is what was used. Now the next example here, before I jump into it, I just want to show you something that could pop up, okay? Instead of showing you the screen and saying bright, dark, they also might show you a graph of the intensity. So intensity for light essentially just translates to brightness, okay? So here it's bright, but it's gonna be a little bit weaker because it's farther out, right? But of course there it's dark, so the intensity is almost nothing. That bright spot's gonna be a little more intense. That's gonna be obviously nothing, okay? Here at our central maximum, we're gonna have a peak, okay? And then of course, low spot at the dark, peak at the bright, but smaller, and peak at the bright. Just wanted to show you that so you'd seen it. That is a fair thing to show. Instead of dark, bright, they could show you a graph of intensity. All right, now it's just asking us to consider what would happen to the spacing of the interface pattern if we used a larger wavelength. So first of all, what does that mean? The spacing of the interference pattern. Which variable is that? Yeah, that's x, right? That's the distance, like this is x, okay? X. Whoops, that wouldn't be x. X is always measured from the central. So that's an x. That's a different x with a different n, okay? All right, anyway, what would happen to x if we used a larger wavelength? So like I said, for just doing these kinds of questions, go ahead and use the approximation, okay? You don't necessarily need to go ahead and find how theta would change. It'll work, just more work than you need to do. So start with lambda equals xd over NL, solving that for x, multiply both sides by NL, and then divide both sides by D. So it's saying, what happens if we use a larger wavelength? Well, we already know, right? Red diffracts more or less than blue. More, right? We saw with the laser. So red, if the wavelength goes up, what happens to x? If I have a bigger number in the numerator, well, x gets bigger too, okay? So increasing the wavelength, will increase the spacing of the interference pattern. In other words, cause it to spread out. Okay, use the larger frequency. So does frequency appear in our equation? No, but wavelength does, right? Changing the frequency, since the speed of light doesn't change, changing the frequency will change the wavelength. Okay, so let's figure out first what that will do to our wavelength with our universal wave equation. So V equals the frequency times the wavelength, and wavelength equals therefore speed divided by frequency. Okay, and so if we increase frequency, what does that mean we're doing to the wavelength? Well, we're dividing by a bigger number here, so our wavelength is going to be smaller, right? So now let's take that to our new equation. We've already solved it for x. I won't bother doing it again. If I have decreased the wavelength by increasing the frequency, well, then I'm going to now have a smaller number in the numerator and therefore a smaller answer for x. So this would decrease the spacing, not spread out, but come together. All right, what if you decrease the slit spacing? So again, that's just the variable d. So what if I decrease that? Well, now I'm dividing by a smaller number, right? I have a smaller number in the denominator. That's going to make my answer bigger. So it will spread out. What if I decrease the distance to the screen? Okay, you could probably think about this. What if I brought the screen closer? What if I brought the screen closer to the diffraction grating? What would that do? You could kind of think about that this way even. Imagine the screen gets pushed to here, right? The bright and dark spots don't go away. It's just now it goes bright, dark, bright, dark, bright, dark. But what if I push the screen to here? Bright, dark. What's happening, right? They're getting closer and closer together. Okay, so you can think about that intuitively, but let's use our equation to check it. So that variable is L. So if I decrease L, okay, smaller numerator, smaller answer, smaller x, right? And so the spacing will decrease. They will come together. Just like we kind of intuitively saw too, right? When we just drew that up there on the diagram of the interference pattern. Okay, so once again, like I alluded to, the math and the physics is really no different for a diffraction grating except for one extra step. We have to figure out D first. So since diffraction gratings are often denoted, as you saw in the last video, by how many scratches are in a unit width, so for example, lines per millimeter, to figure out the space between the lines, D, we just need to take the inverse of that, right? If you have this many lines per millimeter, well then flip that number and you have how many millimeters there are per line, how many millimeters between each line. So, for example, if a grating has 600 lines in every millimeter, what is D, the distance separating them? Well, let's just think of it this way. 600 lines in 1 millimeter. Well, that means in 1 millimeter, there's 600 lines. So go ahead and do that number to get how many millimeters there are for one line, right? 1 millimeter for every 600 lines gives you 0.00167 millimeters between every line. So D is 0.00167 millimeters. Be careful though, right? Standard units, that would be, okay, be careful though. For standard units, we're gonna want meters for this. So times 1 meter is the same thing as 1,000 millimeters. And you end up with 1.67 times 10 to the negative 6 meters is the spacing between each line, or D. Okay, so an X-ray with a wavelength of 2 times 10 to the negative 11 meters, okay, definitely an X-ray, is shone through a crystal with atomic spacing of 3 atom spaces per nanometer. Okay, so in every nanometer, there's 3 atom spaces. Okay, so don't get thrown off by the fact that it's an atom. An atom can act as a diffraction grating. Okay, in fact, you need really small slits for smaller wavelengths, because as that wavelength gets smaller, the pattern gets closer together. The only way to combat that, to spread it back out again, is to bring the slits closer together. This is why we had a hard time figuring out that light was a wave for a while, because we didn't realize how small the wavelengths were. When we were trying to get these diffraction patterns, we weren't using close enough together slits until Thomas Young tried it. Okay, let's just draw this out to get a feel for what's going on here. So we have some atoms acting as a diffraction grating, okay? And it says that in 1 nanometer, there are 3 atom spaces. So 1, 2, 3. Okay, so this is 1 nanometer. It's not D, because D is the spacing between slits, not between 3 slits. A detector is placed 1 meter directly in front of the crystal. So we have our screen essentially, which is just a detector here. Okay, that tells us that L equals 1 meter. And of course, it detects X-rays when it's placed right in front, right? Nothing weird there. It's just coming through basically, the central maximum. but it's then moved sideways until it detects X-rays once more. So see where you have to kind of interpret the physics here as well as the variable numbers, right? It detects it once more. So first of all, are we at a node or an antinode, a bright spot or a dark spot? Right, we're at a bright spot. We're getting constructive interference. Now, the first time we see that, that'll be at, well, n equals 1, right? The central is at n equals 0. So through what distance and angle will it have to be moved for this to happen? So let's just first draw, okay, our central. So there's our central bright spot, n equals 0. We're saying we move it this way until we hit n equals 1. It wants to know what distance did we have to move the detector? Well, we moved it from here where we detected it to here where we detected it again. So it's saying, what is X? And of course, angle, it's saying, what angle did we have to move it through? So what is theta? Okay, so first let's just figure out D. If we have 3 spaces per nanometer, 3 spaces is 1 nanometer, then D is 1 nanometer per 3 spaces, right? I'm just going to go ahead and do the conversion now. That means it's 10 to the minus 9 meters per 3 spaces. And so D equals 0.333 times 10 to the negative 9 meters. That's how many meters there are per space. Well, that makes sense, right? If these 3 Ds add up to 1, right, then each one must be a third of 1, or 0.333, okay? All right, now we've got D. So first let's find theta. So start with lambda equals d sine theta over, do I want n or do I want n minus 1/2? Right, I want n. We have constructive interference. They are one integer wavelength out of phase, not 1/2 integer wavelength out of phase. Okay, so I'm looking for theta. I'm going to go ahead and get sine theta all by itself. If you're okay with that, I'm going to multiply by n over d so that in one step, n cancels, d cancels. Okay, and then I just go ahead and take the inverse sine of both sides. And so theta equals the inverse sine of n lambda over d. I got that theta was 3.4433 degrees. Going to keep some sig digs for later. But the 2 sig digs, it's 3.43. Again, sig digs with angles are kind of weird, but oh well, let's do 2. Okay, now what? Well, we found theta, wants us to find the distance x as well. Okay, so let's go step 2. Okay, and again, tan of theta, right, equals opposite over adjacent. So that's opposite is x, adjacent is L. And so x equals L theta. X equals 1 meter times the tan of 3.4433 degrees. So I got as 0.0602 meters, or x equals, if you'd rather, 6.0 to 2 sig digs centimeters. All right, here's a good one, graphical analysis. Okay, students were asked to determine the wavelength of a laser beam using a diffraction grating. I wish we could have done this in real life. Wish you guys were here. Okay, so the group took the following data. They took, let's just kind of order out which variables we're dealing with here. Okay, so the order number, that is obviously n. Okay, the spacing, so the lines per millimeter, is that D? No, but it's going to tell us D, right? D is millimeters per line, so this is 1 over D. Okay, distance between laser and wall, well, that's the length, right? The distance between the screen and the grating. Distance between antinode and central max. So between the antinode that they're looking at and the central max, that's the definition of the variable x. Okay, and then we need to figure out what's going to go on our x-axis and what's going to go on our y-axis if we're going to graphically determine the wavelength. So whenever we're doing graphical analysis, my tip is think in terms of the equation, not in terms of the data you have necessarily, okay? So let's start with the equation. So starting there, okay, we're trying to figure out how can we get this in terms of variable that we have for data in some way that's meaningful for graphical analysis. Well, what do we have data for? We have data for n, right? We have data for d. In fact, d doesn't change, okay? And we don't have sine theta, but do we have the stuff we could use to get it? Yeah, right? Because theta is just tan of x over L. So we do have data for that, right? Because theta is just inverse tan of x over L. So theta is something we have data for and could incorporate in our graph. So let's play with this a bit. Want lambda. So looking at it here, right? We have sine theta over n. Those are two things that are changing that we have data there. So if we make sine theta our y variable and n our x variable, then this would be, so if So if our y variable is sine theta and our x variable is n, then lambda equals d sine theta over n would equal d times rise over run, which would equal, obviously, d times slope. Okay. Another way to think about this is to play with it till it's in y equals mx plus b form. So we could also have played around with this. So we could have said, I'm going to make sine theta the y variable and then put it into y equals mx plus b form. So that means y needs to be by itself. Sine theta equals n lambda over d. Okay. And look at this. I'm just going to slightly rewrite this just to make it a little clearer. Okay. Look at this. We have y equals m, and n we said was our x variable, right? Really, you should notice that thing first. We have y and x. So whatever this is must be the slope. Plus b. B is 0 here, obviously, right? Because it's not there. Okay. So same result here, right? So then slope equals lambda over d, and lambda equals slope times d. Okay. Two different kind of ways of thinking about it, same result. So let's go ahead and do this. So what do we need? We need to plot sine theta as a function of n. Y will be sine theta, x will be n. I'm going to add another table here because to get sine theta, we're going to need to get theta. Okay, so I'll go ahead and calculate it for every x and L that they've given us. Be careful, one's in centimeters, one's in meters. Got all my thetas. Let's get the sine of all those thetas. Okay, and of course they already gave me the n's. So give an appropriate title and label each axis. So sine theta has no units, right? Sine theta is just a ratio and therefore is a dimensionless quantity. Same goes for the order number. Okay, so we need to go from 1 to 5 on the order number. I count 20 squares, so we'll make every 4 squares an order number. Sine theta, we need to go from about 0 to, let's call it 0.5. So I count 15 squares, so we'll make every 3 a 0.1. Go ahead and plot your data. Okay, and a line of best fit. Remember, don't force it through anything, including points. If it goes through points, that's okay, but you want to represent the trend as accurately as possible, not worry about your agenda. Okay, so that looks pretty good to me. We've got 2 that kind of peek out below, 2 that kind of peek out above. These actually all fit pretty well on the line. So just looking for good spots to use. How about that one? And actually, how about that one? Okay, so we're looking for the slope, so we're going to need rise and run. So the rise equals 0.1333 minus 0.1333 minus 0.066667 equals 0.0. Run equals 1.5 minus 0.75 equals 0.75. And so jumping back to here, lambda equals d times the slope equals d times rise over run, 0.06667 over 0.75. And whoops, we still have to find d. D equals not 150, but if 1 millimeter has 150 lines, and that's 0.001 meters in 150 lines. So D equals 0.00667. Okay, so then this equals 0.00667 times rise over run. I got to 2 sig digs, 5.9 times 10 to the negative 7 meters. Once again, visible yellow pushing orange there a little bit, okay? All right, so it's okay if you're off by a little bit, probably not more than plus or minus 0.3 nanometers. Okay, next one here. Students are asked to perform a standard 2-slit interference experiment with microwaves rather than light. As a microwave cannot be seen, a detector must be used to measure intensity. So we're not going to see the pattern, but we could detect it with our detector here. So what's the procedure? Turn on the microwave transmitter, place the microwave detector at P here, and move it to R in 1 centimeter increments. So move it 1 centimeter towards R, 2 centimeters towards R. And every time you do that, record the intensity of the microwaves. Okay, so we're just essentially mapping out the pattern here. Okay, so let's look at what the question's actually asking. Students were asked to make a hypothesis for the expected result. They were also asked to demonstrate the expected results under wave and particle model of light. And they wanted to look at Young's double slit experiment to compare. So essentially, here's 4 graphs, okay, and it wants us to match them to What would we expect this experiment to look like under the wave model? What would we expect it to look like under the particle model? What did Young see? And what do you think we're going to see? For the wave model of light, what would we see? Well, we'd see an interference pattern, right? Because as we know, we would be splitting light into 2-point sources here, or X-rays into 2-point sources here, and then those 2-point sources would go and interfere with each other. So let's compare 1, 2, and 3, and okay, we can throw 4 in as well. Okay, which one of these shows a diffraction interference pattern? Now notice, look at number 1, right? There's a dark spot right in the middle. That's a low intensity. That's a dark spot, right? Number 2, another dark spot in the middle. That's no good. In fact, I don't know what the difference is between 1 and 2, honestly. Okay, number 3, though, look at that guy. Number 3, there we go. There's a bright spot in the middle, right? And then smaller and smaller intensities as we go out, but bright, dark, bright, dark, bright, dark. So, hey, that's what we should see with a wave model. What about for a particle model? Let's look at the picture again, okay? If light were a particle, particles don't diffract, right? So these particles would go through and they would just like, imagine spraying paint over this. If there was a screen behind them, you would get two kind of slits of paint, but then no paint anywhere else, right? If particles were going through, shooting bullets at this, the bullets would just get through the cracks. So what would you see? You would see some X-rays on the other side, but you would only see them where the 2 slits were. So what graph represents that? Well, looking at graph number 4, right? 2 bright spots, the dark spot in between them where they couldn't get through the slits, but 2 high intensity points where the X-rays were getting through. So for a particle model of light, you would expect number 4. Okay, now it's just saying, what did Young see? So the result of Young's double split. Well, what was Young trying to look for? He was really trying to see if light was a particle or a wave. And what did he determine? He determined light was a wave. So he saw number 3. Okay, now, as we've seen in class, or as I've shown you, right, we've done it. I've produced these diffraction patterns. So we should probably predict for this, because microwave is EMR, just like light, right? We're probably expecting a wave model as well. So 3, 4, 3, 3. Don't ever feel like you always have to use every answer. 1 and 2 are useless here. Now, question here, microwaves are blank than visible light, resulting in a blank diffraction pattern. So knowing what microwaves are is just a memory question, right? You have to know the EMR spectrum. So biggest wavelength to smallest wavelength, we have radio, microwave, infrared, visible, ultraviolet, X-ray, gamma, right? So microwave comes before visible light. Microwave is bigger, right? Unfortunate name because micro usually means small, but again, it's because they're smaller than radio, and radio and micro were kind of the 2 we were dealing with a lot at the time that we named everything. So microwaves are way bigger. They are much longer. They have a much longer wavelength than visible light. So C and D, see you later. Now we just have to decide, would that result in a narrower diffraction pattern or a wider diffraction pattern? Would the bright spots be more spread out or less spread out compared to light? Again, we can use our handy dandy approximation, lambda equals xd over nl. They're essentially asking about x. So if microwaves have a much larger wavelength, what happens to x? Aha, x gets bigger, right? And you saw that with the lasers on the diffraction grating. Red laser was much more spread out than the green laser. Well, it wasn't that much more, but it was definitely more. So they would be more spread out. That means wider, longer and wider. Longer wavelength, wider diffraction pattern. Okay, a group of students investigates interference patterns. The students use a green diode laser to direct green laser light through a diffraction grating. Hey, we did this onto a ruler, placed a fixed distance behind the diffraction grating. So the ruler is essentially acting as our screen here, but it's a useful screen because we can actually measure the distance between antinodes and nodes. Okay. The students adjust the position of the ruler until blah, 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 central maximum hits 0. Okay, so this is the central max. This would be the first order antinode, second order antinode. Okay, and observe the following pattern. Cool. Students continue the investigation by doing 2 more things. So in the first one, the students replace the green laser with a red laser. So you have to know what that means. What variable did we just change? Right, we just changed the wavelength. How did we change it? We went from green to red. What does that do to the wavelength? Red has a larger wavelength. So in this trial, in trial 1, we're making lambda bigger. Okay, we'll save that knowledge for later. Trial 2. Okay, in trial 2, the students replace the diffraction grating with one whose lines are spaced much closer together. Okay, so the lines are closer together. That means the slits are closer together too, right? So what variable is that a change in? We're taking D and we're making it smaller, right? We're decreasing the space between slits. The students use the green laser again, though, to observe the pattern that is created on the ruler. Okay, good students, good science, right? Only change one variable at a time. So if they had changed to a red and changed the diffraction grating, well, now they've changed 2 variables. Good job, students. All right, the row that contains the observations that are expected for trial 1 and trial 2 is. So essentially, how will the pattern change based on the changes they've made to the variables? So when doing that, let's just use our approximation. It's way easier, okay? And so essentially, what's the difference between all of these? Just x, right? The only thing that's changing here, the only thing that's changing in our observations is how far apart the dots are. So we're just looking at x once again. Trial 1, like we said, they made lambda bigger number in the numerator, bigger x. So they should be more spread out for trial 1, okay? So we're going to compare to here. So in trial 1, we saw that x was, or at least to the first one, x was, looks like 13 centimeters. So we want to see the distance from the central maximum to the first antinode be bigger than 13 centimeters. Okay, so 15, yep, that'll do it. A and B look good to me. C and D look no good to me. Let's go back. Okay, trial 2, same formula, just changing a different variable this time. Here we put the lines closer together, so we decreased the D, right? Now we're dividing by a smaller number. There's a smaller number in our denominator, so our answer for x will be bigger. So we're going to have more spread out. So again, something bigger than 13, okay? So no thank you, A. Those are much closer. No thank you, A, okay? But B, yes please. B, you look good, okay? B has a bigger x than 13 centimeters. So B is our answer. Similarly to that other microwave one, in a lab experiment, a microwave generator is used to produce a beam of monochromatic microwaves. Again, monochromatic means one color. I know microwaves don't come in a color, but it just means one wavelength, okay? The waves are incident on a series of metal tubes that form a diffraction grating. So here's our diffraction grating. Notice it can be a lot bigger because microwaves are a lot bigger than light, right? So you can have much bigger spacing and still see a pattern. The metal tubes are spaced 1.8 centimeters apart. So that is our spacing between our slits, right? So that's D, okay. When the microwave signal passes through the grating, a receiver placed 52 centimeters from the grating, so there, right? That would be L, detects a max signal. At the central maximum, we get a maximum. Good, we should. A first order maximum, so n equals 1. Maximum, so we're not going to do n minus 1/2. We're just going to do n, is also detected at each of the positions 1 and 2, as labeled in the diagram below. Okay, well, that's what we would expect, right? Go from the central maximum, and you'll find the first order antinode. Go that way, and you'll find the first order antinode on that side. Note that the diagram is not drawn to scale. So in other words, don't try and take measurements with your ruler. The angle from the central maximum to either position 1 or 2 is 49.8 degrees. Okay, so that is theta. So just ask the experimental wavelength of the microwaves in centimeters is how many centimeters? Okay, careful, that's tricky. In centimeters. Ooh, tricky. Okay, we've got a theta, we've got a theta, we've got an n, we've got a d, right? We're ready to rock and roll. Lambda equals d sine theta over n. We got all that stuff. And plug it in. So you could convert to meters here if you wanted. Notice though, sine theta has no units, n has no units. So if you put your d in centimeters, your wavelength will be in centimeters. Okay, so I'll show you what I mean. Now, honestly, this is kind of risky behavior. I wouldn't trust it too much, but just showing you to get comfortable with the idea of units and when you can and can't do stuff. Okay, first order maximum, so n is 1, and I got 1.37 centimeters. If you had converted to meters, it would have been fine. You just would now have to be careful and put it back into centimeters at the end here, okay? Notice nothing is getting messed with the centimeters here. This is all okay. Okay, so a theory question here. Students use various apparatus to investigate optical phenomena. During their investigations, they make the following 8 observations. Okay, let's first see what it's asking us. 4 observations that could be produced using only a triangular glass prism are what? So we need 4 of these that can be produced with nothing but a triangular glass prism. What can a triangular glass prism do? Pretty much just refraction, right? Yes, dispersion, but dispersion via refraction. It can split white light into a spectrum, but that's just refraction. So, okay, so does the apparatus produce a continuous spectrum with white light? Well, white light, right, remember, is made of all colors, which essentially means all wavelengths. And a continuous spectrum, this will kind of mean more to you after next chapter, but a continuous spectrum is one in which every wavelength is represented from red through to violet, okay? There's not really missing wavelengths or anything. Why would there be? Well, we'll talk about that next chapter, okay? So yes, this is exactly what we saw, right? When we used a prism to split up white light into its components, it made a continuous spectrum, okay? Sometimes called a rainbow, but really it's only a rainbow if it happens in the rain, okay? All right, the apparatus produces a bright line spectrum from white light. Again, this won't mean much to you yet, but a bright line spectrum essentially means there's just one wavelength represented at different bright parts. Why would you get that? Well, you get it mainly from effects that come from the quantization of energy levels in atoms. Again, next chapter stuff, okay? But no. Now, the apparatus produces an interference pattern with monochromatic light. Okay, interference pattern from a prism. Interference, you need to separate light into point sources and then have it interfere with itself, right? There's nothing going on in refraction that's causing that to happen. It's just bending the light, okay? So no there. Does the apparatus produce a single bright line with monochromatic light? Let's think about that. First thing, what is monochromatic? Mono meaning one, okay? Chromatic meaning color, so one color only, right? Like a laser. So imagine this. Remember, refraction, it bends blue light more, red light less, but what if you only have one color? What if you only had red light, for example? Well, it's just going to bend all that red light the same amount. So yeah, it would produce a single bright line, right? It would just make one bright line on the other side, okay? So, and it wouldn't spread it out at all because it would be bending everything the same amount. So that works. That does work. Now, does the apparatus bend red light through a smaller angle than it bends blue light? Okay, don't mix up diffraction and refraction here, right? Blue refracts more than red. Red refracts less than blue, but red diffracts more than blue. So this is saying it bends red light through a smaller angle than blue. So in other words, bends it less. So what would that be true for? Refraction, right? Blue refracts more. But blue diffracts less. So the apparatus bends red light through a larger angle. That's talking about diffraction. So not 6, okay, because this is a prism. It can't do diffraction. The apparatus produces a single spectrum when white light is incident perpendicular to the apparatus. A single spectrum. Well, we already said it produces a continuous spectrum. Did it produce more than one? No, right? There's one beam coming in, it splits it up, and that's it. You get your spectrum out of it. All the wavelengths sorted, all of the colors sorted by wavelength. Okay, we have our 4, but let's look at 8. The apparatus produces multiple spectra when white light is incident perpendicular to the apparatus. Which one was that? That was a diffraction grating, okay? So not 8, right? Remember, the diffraction grating made 2 interference patterns on either side of the central maxima. And if it was white light that was incident, it would get split up into its colors. Okay, so 4 observations that could be made. 1, 4, 5, 7. That totally wraps up topic 3. You're now if you're looking for practice, go ahead and try the specific questions in the Google Classroom or agenda.